All right, we are ready. Okay, so welcome everyone to our second database seminar on blockchain. And today Guna is going to present the mechanics, the inner workings of Bitcoin and blockchain.
So hey everyone, so today's talk is titled Mechanics of Bitcoins and Blockchains. We're going to deep dive into the details of how blockchains works in general, right? So let me start with a quick recap of whatever we saw in the previous lecture, right? So we saw that we have two kinds of transactions in Scrooge coin. The first kind is called create coins, in which Scrooge is allowed to create coins and then allot them to various recipients. The second kind is called pay coins, in which the coin owners can send their the coins owned by them to other recipients and so on, right? So note that the pay coins transaction must contain the signature of all the coin owners, right? So we also saw how Scrooge periodically collects these transactions into blocks and publishes them and maintains what we call a blockchain. So this is important to prevent an important kind of attack that we talked about, which is called the double spending attack, right? So however, we also realized that the currency depends too much on Scrooge and we ended with the question, how can we de-Scroogify this currency and operate without any central trusted party, right? So I'll start the first part of the talk, right? So the first part of the talk is going to be about how we are going to decentralize Scrooge coin, right? So this is the current model we have, right? So when Alice wants to pay some money to Bob, she will create a transaction that says so, signs it with her secret key and sends it to Scrooge. What does it mean to decentralize such a model? Now instead of sending the transaction to Scrooge, she will send it to a peer-to-peer network that is not centrally controlled by anyone. So the P2P network here will be responsible for whatever Scrooge was responsible earlier, right, to maintain a blockchain and to allow only valid transactions to get into the blockchain. So let's unravel this a little more. Inductively, let's assume that this is the current status of the distributed ledger maintained by the network. So Alice will now broadcast a transaction to the P2P network, and so will many others. So each node in the network will collect a set of its own transactions and validate them and create blocks. Note that not all nodes in the network will know about all the transactions, right? So periodically they will execute some kind of a protocol among them to agree on what are the transactions to be included in the blockchain and in what order, right? So finally, after the protocol ends, they create a block that is added to the distributed blockchain ledger, right? So for those of you who are not from the computer science background, we call whatever protocol they execute among them as distributed consensus. And if you're sitting next to a CS student or a researcher, you can ask them about this problem. I bet they'll go like this, because distributed consensus in general is a hard problem, and it is considered hard because it is written with so many impossibility results. So one of the famous examples is the Byzantine generals problem. So it states that two armies A1 and A2 on either sides of an army B trying to attack B can never reliably agree upon a common time to attack if the communication channel is unreliable. That is, if they can if B can capture a messenger that is trying to communicate between A1 and A2 in this context. So another important result is that of Fischer-Lynch-Patterson, which states that any deterministic protocol designed for consensus among multiple nodes will have a possibility of non-termination even if one node among them is faulty, right? So this is not to say that there are no solutions to this problem. So Paxos is a well-known consensus algorithm that solves this problem under certain assumptions, providing certain guarantees. So notice that I said Paxos is a well-known algorithm and not well understood, because everybody thinks they understand Paxos only until they figure out something about it that they didn't earlier, right? So it's quite complex that the original author of Paxos, Leslie Lamport, had to write another paper titled Paxos Made Simple to help the community understand it. In fact, the key selling point of another algorithm called Raft, which solves the same problem with exactly similar guarantees, is understandability. So now let's look at what is the problem, or what are the assumptions under which we have to solve the distributed consensus problem. and we are looking at what is called a peer-to-peer network, right? So there are several features of a peer-to-peer network. To start with, the nodes do not have persistent identities. The nodes can fail at any time. The nodes can also be malicious, and there are also imperfections in the network, by which I mean network latencies and delays in delivering packets. So this problem of, sorry?
What is the node in this graph?
Node is any node in the peer-to-peer network that we are talking about.
What is a node in the peer-to-peer network?
It's just any machine that is trying to participate in the protocol.
The machines.
Yes. So this problem of distributed consensus in a peer-to-peer network in the context of digital cash is believed to be solved by Satoshi Nakamoto, who very discreetly circulated a white paper titled Bitcoin, a peer-to-peer electronic cash system, in a closed email forum. He is anonymous, and the picture I have here is of some other guy named Satoshi, who was alleged to be him by the media. So note that this happened in 2008, and we are already 10 years late to the party. So let's look at what Bitcoin proposed in that paper. So in trying to understand the Bitcoin consensus protocol, we don't want to get distracted by the multiple problems in a peer-to-peer network. So this is going to be our strategy. We'll start with an ideal world, we'll design a protocol for that, and slowly make it real by removing our assumptions. So I must say that this is not how most people teach Bitcoins or explain it. So if you get excessively confused, I do own it, and you should definitely look at other sources if if you get confused. Right. So before we even look at our worlds, let me first answer the basic question. We talk about something called a distributed ledger. So who and how is the data of the distributed ledger across the node, distributed across the node, right? So the answer is everyone in the network has a copy of the entire blockchain, right? This fact makes blockchain tamper proof, because any attacker who now tries to change the data has to change the data in all the nodes, which is highly improbable, right? So now let's get into the first world number 1, right? So here there is a mysterious entity called God, powers we will see shortly, and there are no node failures and no malicious nodes, as ideal as it can get, right? So let's look at how we'll solve distributed consensus in such a world. So transactions, as in Scrooge coin, get broadcast to all nodes. So each node creates a valid block. In each round, God picks a random node n from the network. Since it's God, everyone knows who God picked immediately, right? And now n broadcasts its block bn to every other node in the network, and the other nodes simply accept the block bn and wait for the next round. It's a very simple algorithm, right? So
if transactions are broadcast to everyone, then why they still have to broadcast blocks?
Yeah, so they have to agree on which transactions to include in a particular block, right? Think about the blockchain itself. All the nodes in the peer-to-peer network has to agree on what each block in the blockchain is. They might just have a collection of all the transactions from the network. Yes?
I think the answer is that N encrypts the block. They're signing it, saying that this was accepted.
Oh, okay.
Yeah.
The first broadcast is like a potential candidate to be the next. There is no consensus has been reached by the time of the first broadcast. That's what I understand.
Yeah, so there are a few things to note here. The God choosing a random node provides an implicit consensus in this network. There is no leader election, unlike many other consensus protocols we have seen, and every node in this network trusts every other node in the network, right? In some sense, you could say we didn't actually solve any consensus problem here, and you will be right, but we will build upon this protocol in our future worlds to see how we evolve, right? So if there is any question regarding this protocol, I can answer here. Yeah.
Oh, never mind. We assume no malicious nodes, right?
Yes.
So let's get to the second world number 2, right? So in this world, God exists and there are no node failures, but there can be malicious nodes, right? Let's look at how we'll adapt our algorithm for such a world, right? So similarly, in this world, each node creates a valid block by listening to the clients in the network. Again, here God picks a random node in every round. So n again broadcasts its block bn to every other node. But instead here, each node in turn verifies whether Bn is valid based on the blockchain that it has, right? And it will accept the block only if it is valid. So what do you mean by acceptance? So acceptance of a block is shown by including the block when that particular node gets to extend the blockchain in its turn, right? And what is rejection? They just skip the block Bn and extend the previous block in the chain. Let's see how this evolves, right? So this is a simple peer-to-peer network with 3 nodes, 2 are honest nodes and 1 malicious node. In the first round, God picks the green node, right? So green proposes a block, broadcasts it to every other node in the network, and they all add it to their local blockchains. In the second round, God picks blue node, and the same thing happens. In the third round, again God picks green, and the same thing happens. Now in the fourth round, God is going to pick a malicious node, right? Now the malicious node proposes an invalid block, right? And it broadcasts this block to other nodes in the network. But now what each of these nodes will do is they will in turn verify whether this block is valid or not, and if because it's invalid, they will just throw the block, they will just ignore the block, right? Now again in the next round, God will pick, let's say God picks the blue node. It simply, now the blue node simply extends its local version of the blockchain and broadcasts it. If you notice, now there is a divergence in the blockchain, right? But if we assume a majority of the nodes in the network are honest, eventually the valid chain will survive, right? So is there any question? Yeah.
How does each node verify a block is valid?
Yes, so every node has a local blockchain, a local copy of the entire blockchain. So you can look at the entire blockchain to verify whether a particular transaction is valid or not.
So this assumes like for all the transaction is broadcasted to all nodes.
Exactly.
Okay.
And more specifically, the validity here means first, the hash pointer must be valid, and secondly, there's no double spending.
Yeah, we'll come to all that. Yes.
So this.
Oh, I was just saying, I'm still a little confused about when it got the red block, how it knew to throw it out.
Oh, so you have a local copy of the blockchain, right? You can verify whether a new block, or so when I say verifying a block, it means verifying each of the transaction in the block, right? Okay. When you want to check or verify whether a transaction is valid, a transaction will basically link to previous coins where previous transactions where the owner actually got the coins from. And now if you look at those, you will be able to verify whether those transactions are correct based on your hash pointer, data structures and things like that. Yeah.
I actually have one small question about your figure. Right. So, for example, the new block itself actually contains a hash pointer to the previous one. Okay. Well, this actually means that the hash pointer of the blue one, right, on the malicious node, must have this must be a different block since the hash pointer to it has a hash pointer to the red one, which is bad one.
Oh, I see. Yeah, you're saying the blue one will not be added to the malicious one. Yeah, I think yes.
It's
that's right.
Forked, right?
Yeah,
So,
that's right. So
yeah.
the malicious node will not be able to add the blue block at the end, right? So that's because of hash pointers. Yeah.
So I just want to make sure. So you have the assumption that at each time, every node has exactly the same information.
Yes.
Okay. So there's no delay in the network or something.
I don't assume such things, but the point is only those which have the latest copy will be able to do such things because it's all protected by the hash pointers, right? So yeah, let's move on and it'll get clearer in a while, right? Okay.
So I was just going to ask how does the malicious fork of the chain go away?
Yeah, imagine if it still exists in the network, but majority of the nodes in the network will be acting on the correct or valid blockchain. So it actually only that matters in some sense, right? So let's also look at how the protocol actually handles some simple attacks, right? So let's say the malicious node is trying to steal coins, right? So it cannot in this case because each node, as we saw, each node will independently verify whether the transaction is correct, and essentially the invalid block will be ignored by the network, right? So can the malicious node make a denial of service attack? When I say denial of service attack, what I mean is when it selectively ignores transactions from certain people, right? And again, this cannot happen in this protocol because the malicious node cannot prevent a transaction from reaching other honest nodes in the network, right? So in that way, denial of service attacks are not possible in this network, right? So now let's look at our favorite kind of attack, which is the double spending attack, right? So consider the case where Alice pays Bob in a transaction. It is signed by her. The hash pointer points to a previous transaction where she got the coins from, right? Now if Alice is malicious and she is also running a node, and somehow she is luckily she is the chosen random node in the next round of the protocol, right? So what she can do is she can use the same coins that she gave to Bob and create a new transaction saying I'm going to give the same coins to Alice Prime, right? And because she is the chosen node right now, she can add this node to the blockchain, right? So at this point, both there are two versions of the blockchain itself, right? And both look similar because no one in the network can figure out which came first and things like that, right? So at this point, let's say purely by chance, the next node that is being picked in the random protocol, it extends the one with Alice Prime's transaction, right? So now all the nodes in the network will basically try to extend the longest blockchain available in the network, right? So essentially what happens here is that the block in which Alice pays some coins to Bob is ignored by the network, and that is called the orphan block, right? Because it will never be able to get into the blockchain ever, right? So this is essentially how the Bitcoin protocol prevents double spending attack. Do you have any questions here? Yeah.
Why are both the H's pointing to the very far left node?
Sorry,
Or like
sorry.
the inside of the H of the hash function, if the arrow's pointing to the very beginning?
Which arrows? You're talking about this arrow?
Yeah. Yeah.
Oh, so whenever you saw, so Alice actually has to say which transaction she got the coins from, right? So in both cases she's referring to the same transaction, right? Okay.
There is no total here. There is no account total.
Yeah.
There is nowhere do we have a record how much money you have.
Yes.
Instead, you have all these pointers to all the transactions where you receive the money, and you need to pick one of them to spend the next one.
I'll come to that.
So there's a little trick here. So you can create a transaction that collect all the money, pay to yourself, so you get a total account.
Yeah. So I will come to all that. I have a lot to cover today. So how does it helps to actually think about how does the Bitcoin guard against these two kind of transactions here, right? So one is an attacks here. So one is an invalid transaction that is guarded against by the cryptographic primitives, basically the hash pointers and the digital signatures, and it is enforced by the consensus protocol, right? On the other hand, a double spending attack in this system is prevented purely through consensus, right? Just like how we saw right now. So at this stage, it also makes sense to ask the question, when is a transaction really complete in such a system, right? So as we'll see in the future, in some slides, in some cases it never is complete, right? So however, the confidence that a transaction is complete increases exponentially with every additional block that is added after your block, right? And it is not unusual in the Bitcoin world to actually talk about the number of confirmations for your transaction. Higher the number of confirmations, higher probability it ends up in the longest consensus chain, right? So do you have any questions regarding this world? Yeah.
Confirmation of the number of blocks
That are added
that
after
extend after.
Yeah.
Could you go back to the double spending side with the?
Mhm.
So it seems like here you haven't prevented the attack; you've actually extended the malicious node, right?
It doesn't. So okay, you're talking about from a very moral standpoint of which is malicious and which is not. So imagine in a peer-to-peer network, there is no way to figure out which transaction came first, right? So if you look at the longest valid branch, which is essentially the transaction that has Alice Prime's block, in that block alone there is no double spending, right? And that is what matters, because the other block becomes orphaned anyway, and it is ignored by the network.
Also, the double spending block is marked green here.
So there's nothing like a double spending block here. So the point is, there are two valid blocks that were created at some point in the network, but eventually through consensus, only one of them entered into the longest valid chain. So that is the point here. right? Yeah.
Okay.
So there is no double spending in this network because that blocks becomes out of it.
Did attempt to double spend.
Yes.
So she tried to send to different peers different transactions. One that she spent the same money to Bob, and the other that she spent the same money to whatever, to herself.
I mean,
And hoping that both will make it into kind of local copies of the chain.
Okay.
And then she tries to use the money twice, but whoever the recipient of the money is will wait for several new blocks to be added before he or she can be sure that they got the money.
I see.
Yes.
So it means that like every node should keep a history of all the transactions in order to verify.
In the peer-to-peer network, yes, currently. So okay.
Does anyone have blockchain, block coins?
I have.
How long does it take to start? I heard that it takes several minutes to download the entire log before you can.
Oh, so I can tell you some statistics. In 2013, the entire size of the blockchain was 20 GB around, right, for bitcoins, and today it is around 150 GB.
So that's what you need to have on your computer if you have any block.
No, if you own a block, if you own bitcoins, you don't need to have it. If you're a network, if you're a node that is in the peer-to-peer network, imagine Alice need not be a part of the peer-to-peer network for doing a transaction. She just has to broadcast it to the peer-to-peer networks in the node. So only if you're a node in the peer-to-peer network, you need the entire copy of the blockchain.
miners
Yeah.
onto Erlang.
Well, so I know transactions can take hours to go through. Is there some, like if I'm a company and somebody wants to purchase me with bitcoins, is there some theorem about if you wait X time or something, then it's
Right.
guaranteed that this will be the right?
There's no theorem about it, but people generally assume if you have 6 confirmations, your transaction is almost complete. It's a practical number. That's it.
Okay.
Yeah,
But like if 6 people gained up on me, then they could like.
Yes. Yeah. Exactly.
So if I have like a wallet like contains like a lot of money, like Bitcoin, so is that possible? I can make 2 purchases from that wallet like at the same time, or I need to wait first, like I spend the first money and then wait until that transaction is confirmed and then I can use that money again.
Can you repeat that question again?
So like, for example, I have like $100 like
Okay.
stored in some hash ID. I want to spend $20 to buy one thing and then another $20 to buy another thing.
So
Like,
yes, you have to wait because what you're going to do is in the initial first transaction where you're going to use $20, you're going to send $20 to the recipient, to another recipient, and $80 back to you, right? And if you want to use the rest $80, you have to wait until this gets into the blockchain, and then you can use the remaining $80. Yeah, we'll look at all this in the future iterations, right? So in world number 3, there is no God, and there can be node failures as well as there can be malicious nodes, right? So essentially here we need to answer 2 questions, right? How to choose nodes at random and how to handle failures, right? So Bitcoin protocol answers both of these questions with a single answer, which is proof of work. Note that proof of work is not invented in Bitcoins or by Satoshi. It was first proposed in 1993, and also proof of work is not the only solution to this problem. You might have heard about proof of stake as an alternative. We will look at this in future lectures, but right now we'll just focus on proof of work, right? So let's look at how the algorithm will change here, right? So again, each node creates a valid block. Now, instead of being chosen at random by a mysterious entity called God, each node is going to try to solve a hash puzzle that is based on the block itself, right? Now, if a node n is able to solve the puzzle, it will publish its block bn along with the solution to this puzzle, right? And if the solution and the block is valid, other nodes in the network will accept this block and move on to find a new block and start solving the puzzle associated with the new block, right? So this is how we remove God and also handle failures, right? Not necessarily. So I'll come to what the puzzle is in a moment. So note a few things here. So firstly, the solution to the puzzle is basically the proof of work, and the selection of random node is approximated by selection of nodes randomly based on a resource that is assumed cannot be monopolized, right? In this case, that resource is the computation power that is required to solve the hash puzzles, right? So I mean, there are very few simple questions that we can answer about this protocol, right? So what if 2 nodes solve at the same time, right? So the first answer is it is highly improbable, right? And even if it happens, What matters is the block that gets chosen by the majority of the nodes in the peer-to-peer network, right? So eventually everyone will catch up to that version of the blockchain, and which block will be chosen is determined by randomness and imperfections in the network itself, right? So there is no guarantee that if you solve your puzzle, you are the only one who will be chosen, your block is the only one who will be chosen to extend the blockchain, right? But it's highly improbable. So now let's see what happens when a node, sorry.
Can you go back one slide?
Yeah.
So what happens is, so I want to create a transaction, so that I broadcast to many nodes. Now all of these nodes have to solve this puzzle.
Yes.
They're all solving it at the same time.
Yes.
Why is it improbable that if there's sufficiently many, they might end up solving it in approximately the same amount of time?
The thing is, I'm not solving it for one particular transaction. I'm going to, so basically I'll wait for some time. I will collect a lot of transactions together, right? Imagine this is happening in a peer-to-peer network. So not every node in the network will know of every transaction that is broadcasted, because of all the imperfections in the network, right? So each one will have its own set of transactions. So it's highly probable that you do not have the exact same set as someone else. So the hash puzzle depends on the block. So this hash puzzle is going to be different for different people. Could be, yeah.
So what is the question?
But then, so then there's still kind of this, so in that case, different nodes receive different transactions. They create different blocks with these transactions. They solve puzzles at different times. And then they have to advertise those.
Yes.
So then as a node, I get many advertisements from many people of many blocks. How do I choose?
So you choose the first block that comes to you, right? So you actually are trying to solve a puzzle. In the meantime, someone has solved the puzzle and he is going to broadcast it to everyone. So immediately what you will do is you will accept this block and move on to the next, find a new block and try to solve hash puzzle on that, right? So you wouldn't wait on someone else trying to solve the same block and sending that solution to you.
Spend a lot of time just solving puzzles and never getting to be first.
Yeah, so that I will come to in a little bit, right? So, yeah. Okay, so what happens if the node fails in this protocol, right? So firstly, other nodes will continue to mine, so there is no problem. And whenever the failed node comes back, it is in its own interest to actually learn the current status of the blockchain from its neighbors, right? Otherwise, it's just going to waste resources in mining blocks that no one will accept in the network, right? And if you actually think about it, failure of a node has no impact on the blockchain itself, right? So essentially, the blockchain is maintained by the honest, alive nodes in the network, right? So, any questions? Yeah.
You mentioned that, empirically, if 6 block, extending 6 blocks, and then you know that your transaction is in the previous, the 6th block, then you can get a confirmation that, so for example, if A pays B for a product, and the B only after it confirms that the transaction is in the chain, so B will, for example, give the product to A. But then how will B check? Will B ask every node in the network to get the confirmation, or just to pick some of the nodes to see whether it's in their chain or not? Theoretically, if you want to get the confirmation, you want to know the longest longest chain in the network, right? It's theoretically you have to ask every node to get the longest block, or at least the majority.
Sure. So that is one of the reasons you wait on and actually, so the question, the answer to your question will come a little later, where you have a delay in adding new blocks to the blockchain, so that it stabilizes. And because of this stability within that period, it's highly likely that it has percolated, the block has percolated to all the nodes. So
a stability period is just to make sure that most you hope within this period, most nodes in the network have agreed on the chain.
Right. Yeah.
I can talk a little bit more. I'm not sure whether I can answer the question. I mean, stability is a problem, right? So there are some key design aspects of the blockchain protocol itself. First, the puzzle is designed for generating, the interval of generating a block is 10 minutes. So this is kind of sufficient long for information to propagate that route. And like Gunnar said, it's a miner's own interest to keep update with the newest information, which is longest chain possible in the entire networks. So, and this is still any kind of confirmation here is a probabilistic guarantee. So you can sort of reason about like how, because the six time basically means people think it's the probability is high enough to confirm the transaction. Like,
And
let's
we can go on.
hear about this.
So I'll come to that. So let's talk about what is the hash puzzle that each of the nodes are solving, right? So it looks something like this, right? So basically, what the nodes have to do is they have to find a nonce, which is basically a few bits, such that when you concatenate the nonce with the rest of the block, by block I mean the hash of the previous block and some new transactions that they want to add to the blockchain itself, right? So when you hash this entire string, you want to get a value that is less than a particular target, right? So as we saw in lecture 1 by Shumo, this is difficult to solve, because you do not have a clever algorithm. So the best you can do is a brute force algorithm, and 2, because you have this, you can specify this target. This also is parameterizable, right? We will see how this is handled in Bitcoin in a little while, right? So given that the hash function is cryptographically secure, your best shot is basically to guess randomly, and you keep trying enough nonces until you get lucky and solve it, right? The probability that you'll guess correctly depends on the relative sizes of the target space and the output space of the hash, right? So this process of repeatedly trying different nonces again and again on the hash function is called as Bitcoin mining, right, in the Bitcoin world. So now, what does this mean for two different people who are involved in Bitcoin mining, right? If let's say Alice has 99x more computing power than Bob, what it means is that Alice has a 99% more chance than Bob to be able to solve the next puzzle, right? But in the long run, Bob will basically win 1% of the times, right? And today it is estimated that we have to compute approximately 1.5 into 10 to the 20 hashes per block to add to the blockchain, right? So now let's actually look at how fast does the blockchain grow in a proof of work model, right? So the time to mine the next block depends on two things: the target of the hash function and the total mining power of the network, right? So in Bitcoin network, in Bitcoin protocol, it tries to maintain this value to be a constant, which is 10 minutes, right? As we know, the mining power in the network can vary with time. What they do is that try to recompute the target every 216 blocks, right, which is roughly about 2 weeks. So Bitcoin protocol maintains this 10 minutes essentially to gain the advantages of batching and to stabilize the overall network itself, right? So this naturally leads to the question, what is the throughput of such a system? That is the number of transactions added to the blockchain per second, right? This is quite easy to compute. The time per block is approximately 10 minutes. The block size is limited to 1 MB in Bitcoin, and each transaction takes approximately 250 bytes. So that comes out to approximately 7 transactions per second. And as someone who works on transactions, this number is really heartbreaking. So to give you a sense of how bad this number is, Visa can support 100,000 transactions per second, and even PayPal can support 100 transactions per second during peak traffic. But it is the cost we pay for decentralization, right? So any questions regarding the proof of work model itself? I quickly want to go, yeah.
Just to understand, so if I want to pay you money, and there are more than 7,000 transactions per second, like 100,000, there is a lot of popularity, right? Then I need to pay you over and over. I mean, I don't need to try to broadcast this transaction over and over and over again until I'm lucky that it makes it into a block where I can pay you.
Yes, yeah, there are. That is true, and there are some incentives that you can provide to miners to include your transaction and something, not something else. So I will come to that in a little bit, right? Yes.
Then
yeah.
get a higher
So
priority.
now we get to the next. Laurel, can I answer your question a little bit? Yeah. So now we get to the real world, right? So we all know that mining is expensive, right? And convincing nodes in a peer-to-peer network to solve meaningless hash puzzles is next only to actually training a neural network to learn an identity function just because it's cool or something, right? So, but we know that rational people think at margin, which is a very well-known economic principle, right? So what we're going to do is we're going to incentivize the nodes in the peer-to-peer network to both act honestly and to stick around basically, right? It turns out that our assumption of honesty in itself is a little problematic in your network, right? So let's say a node ends up mining an orphan block, right? In a peer-to-peer network, can you actually penalize this miner, right? Because you do not have any real identities in a P2P network, you cannot actually penalize this miner because he will just create a new identity and join the network again, right? So instead what we will choose to do is we will choose to reward the miners who mined blocks that ended up in the longest consensus chain, right?
I'm sorry, if they reset their identity, don't they lose all the money that's associated with that identity?
Yes. If they had mined an orphan block, they lose all the money, yes. If that was your question.
So can you not penalize them still? Like it would still seem like if you have like, I don't know, $100,000 under that identity, resetting the identity is not.
Oh, so you're assuming that it's a honest node that has mined an orphan block?
Yeah. Or even, right? I mean, they still have.
Sure. I think that needs a longer answer. We can take it offline, right? So yeah. So far we have only looked at the distributed consensus protocol. So now we also know that what we are designing is a currency, right? And currencies tend to have value. So what we can do is we can incentivize these nodes using this currency, right? So let me go over this quickly. There are two incentive mechanisms in Bitcoins. So one is called the block reward. So block reward is so the miner of a block is allowed to include a special coin creation transaction like Scrooge in Scrooge coin and choose a recipient address to whom that coin has to go. And the second is called a transaction fee. So the creators of the transaction, for example, when Alice is paying money to Bob, what she can do is she can make the transaction such that the output value is slightly lesser than the input value, and the rest is considered as a fee for the miner who adds the transaction in the blockchain first, right? And currently it is purely voluntary and it's more like a tip right now, right? So let's look at block reward itself in a little bit more detail. So block reward is in fact the only way to bootstrap the Bitcoin economy, and that is basically to add new coins to the economy, right? So the block reward in Bitcoin halves every 210,000 blocks that is added to the blockchain, right? In 2008 it started with 50 Bitcoins per block, and now it is at 12.5 Bitcoins per, after 10 years it's at 12.5 Bitcoins per block that you add to the blockchain. So as we can see, it is a decreasing geometric series, which means it has a finite sum, right? So this is a chart which basically shows the total size of the total number of Bitcoins that will be in circulation in the network, right? So the first inflection point happened in 2013 where it halved from 50 Bitcoins per block to 25 Bitcoins per block. And we can see it will saturate in 2040 at 21 million. So yes, the total number of Bitcoins can only be 21 million. So a natural question to ask here is why should it actually saturate, right? So the answer to that question is because that's how you create value, right? So scarcity is what determines the value of an item, right? For example, imagine if the amount of gold is infinite, it will not have as much value as it has today, right? So now let's look at the other form of incentive, which is the transaction fees. So as the block reward diminishes, transaction fees will become more and more important. It will become a norm, and then it will eventually become mandatory to add transactions into the blockchain, right? As we can see, the incentive model is constantly evolving, and people are still trying to figure out, what will happen in the future as block reward, completely goes away, right? So Arvind, our colloquium speaker from 2 weeks ago, thinks that or claims that it could destabilize the network. So I recommend you to go and watch his, colloquium talk. So now as a Bitcoin miner, I might be interested to know when will I get my Bitcoins, right? So this can be very easily computed using this simple formula, which is we know that the time to add each block is 10 minutes, and if you know the fraction of your hash power, this will basically be the amount of time you have to wait until you can mine a particular block, right? For example, if you own 0.1% of the hash power, it will take approximately a week to successfully mine a block and basically get the rewards associated with mining that block. So when does it actually make sense to do Bitcoin mining, right? So very clearly when the mining reward is greater than mining cost. So the mining reward in this case comes from block reward and transaction fees, and the mining cost is basically from the hardware investments that you do and the actual running costs such as electricity and cooling.
Probability part. If you have like very little computing power, you're always slower than the ones with like more powers. Then why there still exists some probability that you will.
Oh, so all of these nodes are trying random hashes, right? The probability that you actually get to a value that will solve the hash equation, the inequality equation that you found, is distributed based on how many hashes that you can try on this particular equation.
Assuming like everyone receives the same set of transactions and maybe they create the same block and they at the same time they start computing the hash. Because it's like random.
And by the way, that formula is very approximate, right? A, 10 minutes is not guaranteed, and B, you can never estimate the fraction of hashing power you have, right?
You have a god to tell you the nonce. You just get the nonce for your first guess. Then you can boom, just get your block. Okay, right? Yeah.
Wait, so I know that the reward comes when you're the one who adds the block to the blockchain, but as we've been talking about, it's not always clear even if you get it first, you may not necessarily be the one to actually get it added. So how does the reward, like when do you get the reward?
Oh, I see. So just like how I told you transaction is never complete, you never get your reward completely. So it is still a probabilistic estimate or probabilistic notion of when you have gotten a reward, right? So if you, let's say, have 6 confirmations, you can almost assume that you have gotten the reward. And if any other merchant is willing to accept that you have gotten this reward just based on the 6 confirmations, he can probably use this.
Oh, I
so
get it.
basically the probabilistic notion traverses across the
Oh,
whole.
I get it, because it's added to the block itself. Okay.
So if you're so excited by this prospect of mining and want to straight away get into mining now, I must warn you, this is a very competitive business. People have optimized it to a great extent. So here on the left is a mining farm in China that has more than 10,000 machines mining right now. And these are not CPUs or GPUs. They are specialized application-specific hardware built for hashing. So to give you a sense of how competitive this industry is, they've already released the 5th generation of hardware for the application-specific hashing. And we are still waiting for Intel's NVRAM for almost a decade for doing transaction processing. So that's how competitive this field is.
Just to put some numbers here. So it's 12.5 bitcoins per successful mining every 10 minutes. So
Yes.
10 minutes you have a chance of getting how much? $125,000 if it's at $10,000 or even more, I think it is.
Yeah, it's even more. It's around 14K today and 14K, yeah, almost 180.
You need to guess that with stupid nonce. And if you get it correctly, then it's 100K in 10 minutes. You can understand why they're building all these farms out there.
So,
And there is
But-
a
yeah, now I'll talk about some of the attacks that, how the Bitcoin network actually handles these attacks. So one is,
Transactions fit in the block.
so how many transactions fit in a block? It's 1 MB divided by 250 bytes, whichever the number is.
4,000.
Yeah.
4,000. So that's another bummer. So you want to pay someone, and you don't get into those 4,000. Then you have to try again and again, and you increase a tip. Like if you don't get service, you increase a tip.
So let's talk about Sybil attacks here. So Sybil attack is when one entity in the network actually creates multiple nodes and possesses several entities in the hopes of subverting the protocol and for potential gains, right? So luckily in our Bitcoin protocol, the best they can do is all of them are trying to solve the same hash problem, right? And that means they have a higher probability of solving it, but based on our assumptions, it is okay, right? Because we have assumed no one can monopolize the hashing power, right? But we have to be cautious, right? So let's say such an attack happens, that is, an attacker owns 51% of the computing power, right? So what can such an attacker do, right? So can he steal coins or change block reward, right? So naturally, because he has 51% of the computing power, he will be able to maintain the longest chain in the network, right? However, let's imagine a scenario when the attacker is trying to use these coins against a merchant like Amazon, right? So now let's say Amazon runs a honest node. Because Amazon runs a honest node, it can basically look into its own version of the blockchain and figure out where these coins came from and whether they are valid or not. So Amazon can simply decline, processing his request because the coins had come from an invalid blockchain, right? Another issue is can this 51% attacker actually suppress transactions? Again, this answer is similar to our previous situation. No, it cannot, because other honest nodes in the network can still operate and the transaction can reach these nodes in the network, right? However, a 51% attacker can actually destroy the confidence in a network, in a P2P network like Bitcoin, because you can assume that there'll be a lot of double spending attacks, consensus will be delayed and things like that. So people will decide that they can no longer trust Bitcoin to be a decentralized ledger, and hence they could stop using it, right? So before I get to the next part of the talk, I'm going to try to convey a very important notion about ownership in a Bitcoin network, right? So let's actually try to first understand how does ownership work in real world, right? So let's consider this example where Magda owns this beautiful house in Seattle, right? So so if you ask what guarantees her ownership, she might show you her documents and government records that says she owns the house, right? But if you think deeply, this document means nothing unless the US government vouches to protect her ownership using the various organizations that at its disposal by virtue of this document. So essentially, Magda owns this house as much as the US government is willing and powerful enough to protect her ownership, right? So similarly, let's say Alice owns some Bitcoins in the Bitcoin network, right? Sure, she has a few 0-1 bits that basically says, she got her transaction coins from someone else, right? But again, the ownership is basically guaranteed by the peer-to-peer network that is called the Bitcoin network, and she owns it only as much as the peer-to-peer network can protect it, right? So there is no central party like that of the US government here to guarantee her ownership of the coins, right? So I have to quickly move to the second part of the talk, so I'll skip questions here. Yeah, I know. So yeah, I think I'm going to skip even these things because we discussed all these. So just to give you an idea of how transactions are in Bitcoins, so each transaction has inputs and outputs, and inputs basically refer to previous transactions where you got the coins from, right? And I'll skip all this. So this is how a real Bitcoin transaction looks like, and so there are some things that you can note in metadata. So this is first is the transaction hash, the hash of the entire transaction basically. Then you have some housekeeping information like number of inputs, number of outputs, and lock time. Lock time is a field that we'll look at shortly. So when it is not equal to 0, what it specifies is that a particular transaction cannot be published in the blockchain until that time has passed, right? And we will look at the use cases in a while. And finally, there is some more housekeeping information. So let's look at how each of the input in the input array looks like, right? So it basically contains the hash of the previous transaction where it refers to, which it refers, the index of the output, because that transaction can have multiple outputs. You want to also refer to which output you're going to use here, and finally something that looks like a signature, hopefully that of the owner of the coin, right? And this is how each output in the output array looks like. So naturally it has a value for the output, and then we have something that the field name called script pub key, which reads something like this: op dub, op hash 160, some hexadecimal numbers, op equal verify, op check sig, right? It basically looks like a script. In fact, it is actually a script, right? And in fact, even the input addresses are scripts. So in Bitcoin, what happens is that script sig plus script pub key basically gives you what is known as the verification script to verify whether an input is valid or not, right? So a few facts about the Bitcoin scripting language, which is called script. So it is a very simple and compact language developed for Bitcoins. So it has native support for cryptography, like you saw. Op hash 160 basically hashes the value. It is a stack-based language. It has limits on time and memory, and there are no loops, which also mean that it is not Turing complete, right? So let's look at how the scripting language, so I have basically laid out whatever script we saw there. to figure out, let's say, how it is actually used to verify whether an input is correct or not, right? So in a stack based language, we place value one on top of each other, and whenever there is a command, you execute it top down to basically verify whether it's true or not, right? So here we place sig, then pub key, and op dep simply duplicates the topmost element on the stack, right? So it basically duplicates pub key, and now op hash 160 gives takes the topmost value in the stack and hashes it, right? And now we place the next value pub key hash question mark. So pub key hash question mark is what you got from the output script, right? And now the next command is op equal verify, where it verifies whether the two topmost items are equal, and if that is true, and then finally op check sig basically verifies whether the signature belongs to the same to the public key or not, right? So this is how now this is evaluated. When it becomes true, you can assure that the input is basically a valid input and the signature corresponds to the corresponding output, right? And some more facts about the Bitcoin scripting language. It has 256 opcodes and it supports all these features, right? Basic arithmetic, if then, logic handling, and crypto. So let me quickly talk about only one of the instruction, because we are going to use this in applications, right? So this is basically op check multisig, which takes n public keys and a number t less than n, and it evaluates to true when you give it just t signatures which correspond to t of the n public keys, right? Do you have any questions with this? So you have n public keys, you just provide t signatures out of the which correspond to t of the n public keys, and it evaluates to true, right? So now I'm going to quickly go to the applications because I don't have much time. So yeah, so the first application actually relates to Alvin. So he has been very busy with his PL and database and NLP conference deadlines for a while, and now he needs his garden cleaned. So he goes to a gardener and asks if he can clean his garden, right? And the gardener says, I can, but you have to pay me first. But Alvin is worried. He says, I won't pay you until you clean it. The gardener says, I don't trust you. What if you don't pay me later, right? So let's see how Bitcoin scripts actually help resolve this issue, right? So now to resolve this deadlock, both of them go to a trusted third party, someone they both trust, right? Which in this case is Ed. Now Alvin signs what is called a multi-sig transaction, right? So this multi-sig transaction says that this X amount that belongs to Alvin, right, can be spent when two out of Alvin, gardener, or Ed sign it, right? So it will become more clear in a little bit, right? So now the gardener does his job, and if Alvin is satisfied, himself and the gardener will sign a transaction that uses the X amount to pay the gardener, right? Now if there is a dispute, so Ed will now step in, investigate, and decide whether to give the money back to Alvin by signing a transaction with him, or to pay the gardener by signing a transaction with him, right? So these are called escrow transactions. Now basically we have resolved a scenario where individual parties do not trust each other but still want their services exchanged in some sense, right? So now let's look at the second application, and this second application relates to Bill. After a long day of discussions about linear and relational algebras, he goes back home and is very hungry. He wants food. He calls up his favorite Thai restaurant and says, I need some pad Thai soon, and here's the payment. He also publishes that in the blockchain, right? So the people at Little Thai, they say that, sure, we will wait for 10 confirmations and you will get your food in 2 hours, right? But that leaves our Bill hungry for 2 hours, which is not ideal. So let's see how we can fix this, right? So to help ease such transactions, we bring in another third party called, let's call it bank here, right? So these banks own and operate what are called green addresses. These addresses are known by merchants to be honest and not involve in any double spending. So any merchant can easily verify this by running a node itself, right? So instead of Bill directly paying Little Thai, what Bill says is he asks the bank to pay Little Thai on his behalf to basically make a green payment. So now the bank pays Little Thai using one of its established green addresses, right? And Little Thai is now happy that, okay, this is a payment from a green address, I trust this, so I will process the order immediately, right? So now Bill is happy. So note that in this application, there are several things that happen outside the Bitcoin network itself, right? Such as Little Thai trusting the bank and bank facilitating Bill's transaction, right? So it is in the interest of the bank to gain trust among all the merchants, because the bank can eventually charge Bill for such a service, right? Now we have a third application which is called micropayments, and if you have not guessed it yet, this relates to Dan. So now Dan wants to get a new mobile connection. He goes to AT&T and AT&T inquires about the plans, and AT&T tells him that they have a plan in which Dan has to pay immediately for every call he makes, right? Now, but Dan knows that this can be very expensive now that transaction fees are going up. So he proposes a slightly different solution. Let's see how he uses Bitcoin scripts to solve this, right? So now, before AT&T starts the service, Dan signs a multi-signature transaction that specifies that some specified amount, 100 coins that belong to Dan, can be spent by any other transaction that has both the signature of Dan and AT&T, right? So you can assume 100 coins as an upper bound on the total amount of service that AT&T is going to provide Dan. Now, after the first call Dan makes, what he does is he additionally signs another transaction that consumes the previous 100 coins and gives 1 coin to AT&T and the rest 99 to himself, right? He gives this partially signed transaction to AT&T. AT&T stores this transaction but does not publish it in the blockchain yet, right? So now Dan makes another call. He does something similar. He signs another transaction that says pay 2 coins to AT&T and the rest to myself, and he does this similarly for every coin, every call that he makes. Finally, when he is done with the service, what he says, no, I'm done with the service. So now AT&T will basically take the last transaction that Dan signed partially. AT&T will now sign that particular partially signed transaction and publish it in the blockchain, right? So essentially, we have reduced so many other transactions, so many micropayments into just these two simple transactions. Only these will eventually get into the blockchain, right? So yeah, so there is a very natural question: what if AT&T, publishes 2 of the transactions that Dan partially signed, right? So you know that. So if you think about it, each of the transactions that Dan signs is basically a double spending, right? And you know that the Bitcoin network will eventually figure out that only one of them will get into the longest consensus chain. So it is actually in the interest of AT&T to publish only the latest transaction that Dan signed, right? Now there is a problem with this model, right? So what if AT&T, instead of saying cool, I'll publish your latest transaction, it just says cool, bye. Now, and it does not publish any of his submissions, right? Now Dan will not be able to get back his remaining 58 coins, right? And he will not be able to spend it anywhere else, because if AT&T does not publish the transaction, that will be inaccessible, right? But we all know Dan is smart, so he has a solution to this, right? So right when he signs the initial multi-sig transaction, he asks AT&T to sign a transaction that pays back Dan the entire 100 coins, but with the additional clause that it is locked until 1 year. And we do this by using the field that we saw in the metadata, which is called the lock time. So what lock time does is that it specifies that this transaction cannot be published in the blockchain until this time has occurred, right? So now, in case AT&T did not publish any of his partially signed transactions, Dan will simply take this, sign it, and publish it in the blockchain, right? So now here Dan has a leverage to say that AT&T has to publish whatever he submitted latest, right? So this is the end of our third application. And we're going to talk more interesting things about such ideas and applications based on more advanced Bitcoin scripts. This will be we will talk about this in the next lecture on smart contracts, right? So I'm already out of time, so I will just quickly summarize whatever we saw today. We have looked at a lot of interesting ideas today. So the first part of the talk, we focused on decentralizing Scrooge coin, how the Bitcoin blockchain evolves, how proof of work helps us solve distributed consensus in the presence of failures and malicious adversaries, and finally how the incentives play an important role in Bitcoin network in the stability and maintenance, right? And in the second part of the talk, we looked deeper into Bitcoin transactions, understood how the inputs and outputs together form a verifier script, and finally we saw some applications of Bitcoin scripts that help us develop cool new applications, right? So that's the end of my talk. And
we are running out of time. We don't have time for questions. So please join us next week. You're taking